Dear students, today we will verify the last three properties of DFT which we have studied in last class. In that, first we will take verification of circular frequency shift property. Example, given x of n equal to 1, 0, minus 2j, 2 plus 3j. For m equal to 2, verify circular frequency shift property of DFT. Solution: x of n is equal to 1, 0, minus 2j, 2 plus 3j. M equal to 2 and capital N is equal to 4 because there are 4 samples, 1, 2, 3, 4. First we will calculate e raised to j2 pi mn by capital N. For m equal to 2 and capital N equal to 4, we get e raised to j into 2 pi into 2 into small n by 4. 2 into 2 is 4 and that 4 will cancel with 4 in denominator. Therefore, we get e raised to j pi n. Here, n values are 0, 1, 2 and 3. For these three values, we will find e raised to j pi n. So, e raised to j pi n is equal to, if I put n equal to 0, e raised to 0 we will get, e raised to 0 is 1. If we put n equal to 1, e raised to j pi we get. E raised to j pi means cos of 180 degree, that is minus 1. For n equal to 2, we get 2 pi. 2 pi means 360 degree or 0 degree. So, here we get plus 1. Next, for n equal to 3, e raised to j 3 pi we get. E raised to j 3 pi is minus 1. Now we will calculate x of n into e raised to j2 pi mn by capital N or 4, because capital N is equal to 4. Multiplying sample by sample, we get the product of x of n and e raised to j2 pi mn by 4. So x of n into e raised to j2 pi mn by 4, that is equal to 1 into 1 1 minus 1 into 0 0, 1 into minus 2j minus 2j, minus 1 into 2 minus 2, minus 1 into 3j minus 3j. Now we will calculate the DFT of x of n into e raised to j2 pi mn by 4. That is, we will calculate the DFT of frequency shifted x of n. That is, we will calculate the DFT of circularly frequency shifted x of n for m equal to 2. So now write here DFT of x of n into e raised to j2 pi mn by capital N or 4 is equal to this is x of n into e raised to j2 pi mn by 4 matrix. It's a column matrix. 1 0 minus 2j minus 2 minus 3j. It is total factor matrix. One, one, 1 1 1 1 1 1 minus j minus 1 plus j minus 1 plus 1 minus 1 plus j minus 1 minus j. Multiplying these two matrices, we get equal to minus 1 minus 5j 4 3 plus 1j minus 2 plus 4j. Now this is LHS for us. Now we will compute DFT of x of n. We will make use of matrix method only because it is fast method. X of n is 1, 0, minus 2j, 2 plus 3j. Total factor matrix 1, 1, 1, 1. 1, 1, 1, minus j, minus 1, plus j, minus 1, plus 1, minus 1, plus j, minus 1, minus j. Multiplying these two matrices, we get 3 plus 1j minus 2 plus 4j minus 1 minus 5j and plus 4. After this DFT computation, we will calculate circularly shifted x of k by 2 units. DFT of x of n means what here? It is x of k for us. Now we will compute x of k minus m shifted circularly mod n. Here n is equal to 4. For m equal to 2 and n equal to 4, that is x of k minus 2 mod 4 if I shift 4 by 2 samples, first time it will go to the place of 3 plus 1i, then it will go to the place of minus 2 plus 4j. So 4 will go to this position. Then minus 1 minus 5j will also be shifted by 2 samples. When shifted by 1 sample, it will go to the position of 4, and when shifted second time by 1 more sample, it will go to the position of 3 plus 1j. So minus 1 minus 5j we will get here. Now below 4 will have 3 plus 1j, and below 3 plus 1j we will have minus 2 plus 4j. This is now RHS for us. Since LHS is equal to RHS, you can compare LHS and RHS, you will find them equal. Therefore, now we'll write, since LHS equal to RHS, circular frequency shift property of DFT is verified. Next we will take multiplication property of DFT. Given two 4-point sequences x1 of n equal to -1, 0, 2, 3 and x2 of n equal to 5, 2, -1, 0, verify multiplication property of DFT. Solution. Given x1 of n equal to -1, 0, 2, 3 and x2 of n equal to 5, 2, -1, 0. Here n is equal to 4 because there are 4 samples in each of the discrete time sequences. To verify multiplication property of DFT, first we will compute x1 of n into x2 of n by multiplying corresponding samples. So x1 of n here, x2 of n here, -1, 0, 2, 3, 5, 2, -1, 0. x1 of n into x2 of n is equal to 5 into -1, -5, 2 into 0, 0, -1 into 2, -2, 0 into 3, 0. Next we will compute DFT of x1 of n into x2 of n. So right here DFT of x1 of n into x2 of n, that is equal to, use matrix method, 1, 1, 1, 1, 1, 1, 1, 1, minus j minus 1 plus j, minus 1 plus 1 minus 1, plus j minus 1 minus j. into the product of x1 of n and x2 of n, which is minus 5 comma 0 comma minus 2 comma 0. Multiplying these two, we get minus 7 comma minus 3 comma minus 7 comma minus 3. I will write this equal to sign here. Now this is LHS for us. Now we have to prove that this LHS is equal to RHS, where RHS is equal to 1 by n into circular convolution of x1 of k and x2 of k. So now we will compute first DFT of x1 of n, DFT of x1 of n. One minus j minus 1 plus j minus 1 plus 1 minus 1 plus j minus 1 minus j minus 1 0 2 3. The product of these two matrices is equal to 4 minus 3 plus j3 minus 2 minus 3 minus j3. Similarly, we will compute DFT of x2 of n. DFT of x2 of n is equal to total factor matrix into x2 of n. So 1 1 1 1 1 1 1 minus j minus 1 plus j minus 1 plus 1 minus 1 j minus 1 minus j. x2 of n is equal to 5 2 minus 1 0. Multiplying these two, we get 6 minus 2j 2 6 plus 2j. Students, because of the timings, I am not showing how to multiply the matrices. You being third year engineering students should be able to operate your calculator in complex mode and find out these products. You please practice this at home, otherwise in examination time will not be sufficient for you to compute and get correct results. Now we have to convolve circularly DFT of x1 of n and DFT of x2 of n. We will call DFT of x1 of n as x1 of k and DFT of x2 of n as x2 of k. Now we have to compute x1 of k circularly convolved with x2 of k where n is 4. You have learnt computation of circular convolution of two sequences in signals and systems. There you will be shifting one sequence by one sample every time. That is, in the first column you will write x1 of n as it is. See here, 4 minus 3 plus 3j minus 2 minus 3 minus 3j. Now this last sample you will write as first sample, minus 3 minus 3j. Then first sample you will write as second sample, second sample you will write as third sample, and then third sample you will write as the last sample, that is minus 2. Similarly, now you will take this minus 2 here and all these elements you will push down by one row. Minus 3 minus 3j, 4 minus 3 plus 3j. Minus 3 plus 3j, minus 2, minus 3 minus 3j, 4. And the second sequence will keep as it is. That is 6, 6 minus 2j, 2 and 6 plus 2j. After multiplication we get minus 28, minus 12, minus 28, minus 12. Now we will compute 1 by n into x1 of k circularly convolved with x2 of k, that is 1 by 4 into minus 28 minus 12 minus 28 minus 12, which will be equal to minus 7 minus 3 minus 7 minus 3. Now this is RHS, since LHS is equal to RHS, multiplication property of DFT is verified. Now we will take an example for verification of circular convolution property of DFT. Given x1 of n equal to -1, 0, 2, 3 and x2 of n equal to -5, 2, -1, 0. It may not be visible to you because of that KineMaster watermark. You can now write. Okay. Verify circular convolution property of DFT. Solution. First we will compute the circular convolution of x1 of n and x2 of n. So right here x1 of n circularly convolved with x2 of n equal to, in one matrix you have to write circularly shifted x1 of n, and in another matrix you have to write x2 of n. So this is x2 of n here, 5, 2, -1, 0, and here we'll write -1, 0, 2, 3. Now this 3 will go here, -1, this 0 here, and this 2 here. Next 2, 3, -1, 0, 0, 2, 3, -1. By multiplying these two matrices we get circular convolution sum of x1 of n and x2 of n, and that is -1, -5, +11 and +19. Next we will compute DFT of x1 of n circularly convolved with x2 of n. So here you write DFT of x1 of n circularly convolved with x2 of n. One, 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 -j, -1 plus j, -1 plus 1 -1, j, -1, -j. So this is Studel factor matrix, and here now we have to write x1 of n circularly convolved with x2 of n result, that is -1, -5, 11, 19. Multiplying these two matrices, we get (24) minus 12 plus 24j minus 4 minus 12 minus 24j. Now this is LHS for us. Now we have to compute the DFTs of x1 of n and x2 of n separately and then multiply DFT of x1 of n with x2 of n sample by sample. We have already computed DFT of x1 of n and x2 of n, so we will make use of those results here directly. DFT of x1 of n is equal to 4 minus 3 plus 3j minus 2 minus 3 minus 3j. Let us call this as x1 of k. DFT of x2 of n equal to 6 minus 2j 2 6 plus 2j. Let us call this as x2 of k. Now we will multiply x1 of k and x2 of k sample by sample. You will have to make use of your calculators because it is multiplication of complex numbers. 4 minus 3 plus 3j minus 2 minus 3 minus 3j 6 minus 2j 2 6 plus 2j. Remember, it is not matrix multiplication, it is multiplication of corresponding samples. So when you multiply the corresponding samples, you will get (24) minus 12 plus 24j minus 4 minus 12 minus 24j, and this is RHS for us. Since LHS is equal to RHS, circular convolution property of DFT is verified. We will stop here and continue in next class.